So welcome to the WWS show. Today we are going to discuss about the sum of infinite natural numbers. So how it's negative 1 by 12 and why it could be wrong. So first we'll start with the proof given by Sir Ramanujan, and he has said and proved that sum of infinite natural number is negative 1 by 12, and see the proof step by step how he arrived to that conclusion. So natural numbers, we already know, start from 1, 2, 3, 4, 5, 6, so on. And the sum of first n natural number is given by n. This formula here, you can see here, this formula. So it's given by this formula, n into n plus 1 divided by 2. And the sum of infinite natural number, well, that's what we are trying to get here using the Ramanujan's proof. So it uses the infinite sum of two series, and first series is this S0, which is alternating between the 1 and negative 1. Second series is S1, which is 1 minus 2 plus 3 minus 4 plus 5, although it seems the same as the sum of the natural numbers, but the sign is alternating between negative and positive. So we first need to find the sum of infinite sum of these series, then only we can find the infinite sum of the natural numbers, right? So how exactly we are going to compute? So to compute S0, the infinite sum of this series, so if you see the pattern here, if you have the even numbers, even terms in the series, then the plus 1 will cancel out negative 1, you know. And in the same way, if you see that the sum of the even terms will turn out to be 0. For example, sum of the first two terms will be 0, sum of the four terms will be 0. As you can see, they are already cancelling out. And the sum of, if you have the odd terms, or if you have the odd number of terms in the series, then the sum will be 1 instead of 0. For example, sum of first three terms, here the first two terms will cancel out, you will have only 1. And based on that, if our infinity is uh, giving us the odd number, so we have these infinite numbers, and if the number of terms we have, if they are even, then we'll get the total sum 0. If they're odd, then we get the total sum 1. Now we we see we're oscillating between 0 and 1 throughout our journey to infinity, and at infinity you could have either 0 or 1 as your sum. So we'll take the average of 2, and that will have our answer. So answer will be 1 by 2. So how exactly we're going to compute S1? S1 is rather different from S0, and you can see we cannot apply the same trick we applied for S0. And because it's not oscillating between the two fixed values like S0, so we instead do another trick. Here we take the series two times. So in this first, you can see we have the series S1, 1 minus 2 plus 3, of course. And again we take the series S1, right? And but it is shifted one digit to the right. So this is really our shifted series, right? Now if you going to add them, if you're going to add these two series, so you will get 2s1 is equal to 1 will be as it is because there is 0, minus 2 plus 1 will give minus 1, plus 3 minus 2 will give plus 1, negative 4 plus 3 will give you negative 1. So you will alternate between 1 minus 1, and you got this series which is equal to s0 because we have dealt with it. Since we know the sum of these this series, which is 1 by 4, infinite sum is 1 by 4, so we can compute s1 as well, because 2 in times s1 is equal to s0, so s1 is equal to 1 4. So now we have computed the sum of two series which were required to find the infinite sum of natural numbers. So to compute this now, the series here, which is sum of natural numbers, right? We apply this another trick using S1, right? So here we have S1. Now we negate the S1. Okay, so we have negative 1 in this place, plus 2 minus 3 plus 4, right? Negation of this S1 is there. Now we have our series we want to compute, a normal series of natural numbers, right? 1 plus 2 plus 3 up to infinity. Now, if you're going to add these two series, this negative s1 plus your normal series, right? S. Now s plus s1 will give you 0 plus 4 plus 0 plus 8. And now if you analyze this series and take 4 as common, you will see you will get this series which is the sum of natural number. It is the same as s, right? And if now we substitute in this place s and solve for s, we know that s1 will be 1 by 4, right? So s1 is 1 by 4, and now if you solve for s, then you will get negative 1 by 12. So that's the proof given by Sir Ramanujan. Now we or me, I want to pinpoint the problems in this solution. First thing is that the sum of infinite natural numbers is supposed to be at least positive, because we are summing up the positive numbers. So the negative sign clearly adds up to absurdity, right? So the first term, and the second problem I have is that the first term is 1, the rest terms are greater than it. So how could we end up with some fraction? Now I don't know how we could end up this fraction, but the major problem I see is at least the sign. So let's try to solve this mystery. Now first I will define the infinity, like how I think infinity works, and based on that we will see that Ramanujan's solution could be wrong, and I will propose my own solution to that, right? So we will get to know what exactly is infinity. Is it a number, or are we supposed to reach it in the first place? Okay, so let's start with a simple game. So Frank is my student and he likes to play a game. And the game is about that Frank will generate some numbers and I will explore those numbers. So I told him to generate number and he generated me around 10,000 numbers, right? And I will explore those numbers one by one, starting from 1. And right now I have explored up to 100 numbers. Now, eventually I will reach the Frank, and clearly I will be sad because there will be no number for me to explore, right? Now here what Frank will do, then it will generate more and more numbers, but each time the supply won't be enough, and so I would end up reaching Frank with no more number to explore anymore, right? So it doesn't matter how much the Frank generate, how big the number is. Eventually, I will end up exploring all of them and reach Frank. So the problem that Frank is running at is that is not being able to generate the endless supply of numbers for me to explore. And clearly, after generating a very high amount of numbers, you think he is at infinity, but he's not, right? And so here Frank comes up with an idea instead. He says that instead of generating a whole lot of numbers and sitting idle, why don't he generate number dynamically? That is, generate them dynamically while I explore them, right? So while explore, Frank will generate instead of sitting idle. So here the Frank has just generated 101 and I will explore the previous number it has generated 100. Now I will explore 101, the Frank will generate 102. Now I will explore 102, Frank will generate 103. In the case, the Frank is moving with me. As I'm exploring, Frank is generating. Frank is not very far away from me. He's very close to me instead. He's just one step away. But still it is giving me the illusion of infinity. Now that is what infinity is, my friend. In this definition of infinity that I've given you is what I think or I believe infinity should be. Because here the M, me, the M, capital M refers to me and F refers to Frank. Here with respect to me, Frank is at infinity if Frank is moving at the same rate or Frank is generating the number at the same rate as I'm exploring them. So we can summarize this up with these points that if the rate of me exploring and the rate of Frank generating is same, then the f is at infinity with respect to m. That's important. With respect to m, f is at infinity. Now here m could be greater than the rate of me exploring would be greater than m. Then here f is definitely reachable. Other than that, here f is at diverging infinity. You know, if the Frank is generating his rate of generating is greater than me exploring, right? So with respect to me, he will be diverge. So now we are ready to actually go through why the proof of Ramanujan could be wrong. We are on the path to it. So we have represented the S0, which is 1 minus 1 plus 1 minus 1, this series in the waveform, right? So this is the plus and this is the negative. So plus portion, negative portion, we will alternate between them. And to get the sum, we will just sum up the area under this square wave, right? Here F represent the marker for Frank, M for me, right? And similarly, down there is also a similar same wave actually. For it, the F marker lies one step ahead and M is here, right? Now in this case, the f here will leads to even sum because it is at even step, and even sum lead me to 0, right? In a similar way, the f marker in this babe this babe down here will give me 1, the odd sum, right? Since it's one step ahead, it's at odd position, so it will give me odd sum, right? So here the two infinity, actually infinity is just a way to say it, but we call them f sum, right? So two f sums, they are different here. One gives the odd sum, other gives the even sum. Now let's say we have two systems. This system up here, the system down here. We call them upper system, upper wave system, and lower wave system, right? Now the two systems could be connected and could be disconnected as well, right? And it should be noted that disconnected systems, they are by themselves. They are all, they are not connected to each other, they are not linked, right? So but in the connected system things change a lot. If these two systems, if they're connected, then their f marker, they will be connected as well. And the important thing to note that the m marker will be same for both the system. And since the m marker cannot pass this f marker in the first wave, it can never pass the f marker in the second wave as well, right? And since it can't even pass the f marker in the first wave, mean the sum, the f sum, it will be same in both the cases, right? So it doesn't matter where the f marker lies in the second wave, as long as the two systems are connected, the closest marker from both the waves will be considered the f marker for m, will be considered something called infinity with respect to m. And with that, both sum will be equal. So since f1 was giving the even sum, so here in both the cases the f sum will be 0, right? And if f marker was at even odd position, then the f sum would be 1 for the both cases. So now since we can have f at odd even position and can have f at odd position, so we can get two f sums for even and odd. What we do is do the average of them and we'll get the net f sum. Now this whole structure of doing things, right? This whole way of finding the even f sum, odd f sum, and taking the average to get the net f sum, it's very important. It is a fundamental assumption that leads us to solution. Even Ramanujan had took the same assumption. He did get the zero sum and one sum. He called it the infinite sum, right? For the even infinity and odd infinity. And then he took the average to get the net sum. Same assumption has been taken here. Now, if we go further, now we'll do the similar process for S1 series, right? And so this expression here, we already know what this expression is. Here, S1 series plus S1 shifted, it will give us S0, right? So we saw it in the previous slides that if you add S1 with S1 shifted, you will get S0. So you can see down here the waveforms, and this is S1, this is S1 shifted. Now adding them both, so 1 0 will give 1, minus 2 plus 1 give minus 1, 3 minus 2 will give 1, and so on, right? Now we'll consider a system that is disconnected. So if the system is disconnected and if you want to find the f sum which is even, so f marker will be at even position, right? In the both cases, for S1 even position, for S shifted, it will be shifted as well, the f marker, right? Because only then the sum will be same, right? If the system is disconnected, then the sum will be same, right? Now, since the sum is disconnected, can take the f sum individually without interfering these infinity with each other, right? You don't have to worry about taking the common marker here, right? And with that, you can find S0, S1, and S1 star f sum. So f sum of f will turn out to be 0. F sum of f sum turn out to be -3. F sum of S1 star turn out to be -3 as well. They both are same in this case, right? And for the disconnected system, now we'll take f sum odd. So now here f marker is at odd position. Again we do the f sum. It turns out to be 1 for S0, turn out to be 3 for both S1 and S1 star, right? Now for a disconnected system, we get the even f sum for s0, s1 or s2, for both of them it is same, s1 star and s1. So we get it 0 comma minus 3. For odd f sum we get uh, the odd f sum for s0 and s1 or s1 star we get 1 3. Now we know that what we do is that we get the odd f sum, even f sum, do the average of them. So we do the average for s0, we get 1 by 2. For s1 or s1 star we get 0, right? So in this case you can see where a disconnected system equation is being not satisfied. So you can definitely add s1 s0, which is both 0, and 0 is 1 by 2, which is not, correct. But similarly, if you do it for a connected system, then the thing changes. For connected system, you get the f sum even for s0, s1 and s1 star. So you see we have the f marker at even position, right? This is a shifted one, but now systems are connected. So with this, m will be common for all of them, and with respect to m, only one f marker will be considered infinity, right? So f sum for s1 star, s1 or s0, it can go past this f. So you can find the f sum with this single marker for all of them. So this f marker, you know the same f marker will be followed for by all of them, by all of the waves, to get the final f sum. So f sum with respect to this marker will be 0. F sum with respect to the same marker will be minus 3 for s1, for s1 star. F sum with respect to this same marker will be 3. So you can see here the s1 or s1 star both giving the different results, right? Now if the systems are connected, now you want to find f sum odd, right? So for s0, s1 and s1 star, we get the f sum 0, 3, minus 2. Similar procedure, this f marker will be same for all of them, m marker will be same for all of them, and based on that you can calculate the f sum, which is turn out to be 1, 3 and minus 2, right? Now you will get the you will have the even f sum for three of the waves. You will have odd f sum for three of the waves, right? Now you get the average of them. So average of s0 turned out to be 1 by 2, and that's correct. We did get the value 1 by 2 in our case. In the connected system we saw this thing, right? For this way we did get the f sum of s0 1 by 2. So f sum of s0 indeed is 1 by 2. So now for s1, for this we'll get it's 0, and for the s1 star we'll get the 1 by 2, right? So we get the net f sum for s0, s1 and s1 star, and we saw that net f sum of s1 and s1 star is not same, they are different, but the equation does hold. When you add s1 to s1 star, you did get 1 by 2, but clearly s1 and s1 star, they're not equal. Now keep in mind, when two systems are disconnected, f sum of s1 and f sum of s1 star, they are equal, but when they are connected, then that's not the case, they are not equal. So now here we have the f sum of s1 and s1 shifted, which is actually the s1 star. Now this f of s1, f of s1 shifted is equal to f of s0. Similar equation here, same equation is being used. Here f of x is simply the sum of x, right? So these are f sum of s1, f sum of s1 shifted equal to f sum of s0, right? So for a connected system, these two are not same. So we cannot say the f sum of s1, f sum of s1 shifted is equal to 2 f sum of s1 or 2 f sum of shifted, because they are different. So we say it is 2 times some k value. So k turns out to be the sum of them divided by 2. Okay, so to find the value of k, You need the f sum of s1 and f sum of s1 star. We know both the value. This is 0, this is 1 by 2, and we'll get 1 by 4. And we indeed get 1 by 4 in our solution given by Ramanujan. He did tell that this k, but what he did wrong here is told you that this k is actually the f sum of s1. That's what he told you, right? And that is indeed wrong because it's not. Also, you can prove it from the right hand side. K is f sum of s0 divided by 2, and f sum of s0 is 1 by 2, so k will be 1 by 4. So k satisfies. So k is 1 by 4, but k is not f sum of s1, nor it is s1 shifted. But he did told you that it's f sum of s1, right? So that's kind of wrong. So further, fortify why it could be wrong is that for the equation s minus s1 is equal to 4s1, if we have a connected system. So let's say we have a connected system. We got this result from a connected system, and we further follow it in a connected system. So we have the S series, the series of natural numbers, the negative S1. Okay, so you have just negated the S1 series. So we have minus 1, 2, minus 3, 4, up to so on. And then if you just add these two series, element wise element, you will see 1 minus 1 0, 2 2 4, 3 3 0 4. Here 4 is taken as common, and then we'll get this series. So in this case, again a connected system is there. F marker will be same, M marker will be same for all of them. You can see that the F sum for this one is clearly less than F sum over this one. You can actually see it. And but the Ramanujan said that it's same. He told you S minus S1 will give you 4 times S, and this S is same as this. How could that be true, right? So 4S minus S1 is equal to 4S1. Actually, it's in this form, S minus S1 equal to 4 times S naught. Okay, so it's not same because F sum of S is not same as F sum of S0 by considering the connected system. Thus, F sum of S minus 4, so you just rearrange the equation, is equal to this. According to Ramanujan, these two things are same, so he take them L. That's what that L. So L minus 4L is equal to S1, so L is minus 1 by 12, which L is not Fs. Clearly, you see L is not Fs. So under the disconnected system, you can say that S minus S is equal to 4S. This equation is only true under a disconnected system, while it's not true under a connected system. Under a connected system, this is true. S minus S minus is equal to 4, S 4 into S naught, right? And we saw that these result that we got, K is equal to 1 by 4, that result is only true if we say that K is the average of f sum of s1 and f sum of s1 shifted, and divide by is the average of this. Then let's say we consider it's true, it's a net value of this s1 waveform, right? Then that's only true if the system is connected, right? But if the system is connected, then this equation is false. This is only true when the system is disconnected. So half of the proof goes in connected system, and the final equation that he gives, from the disconnected system. It's very clear, and that's what the result is so absurd. Now I will give you my result. Okay, so now if the key is considered correct, and why, let's see. So average of fs1, f sum of s1 and f sum of s1 shifted, star, it gives you net f sum, and it could be considered true based on the fact that we were doing the average of even and odd f sum. So we can use the same analogy to get the net fsum. Second thing, which implies that if s and s naught, if they're not same, then the average of them could give us net fsum. So we're using the average, right, to get the net fsum. So which means the s naught plus s divided by 2 will give you net fsum. And this equation, we already know it is true in a connected system. S minus S1 is equal to 4 times S naught. And finally, since Sn is greater than S naught, that's what we implied, that the final sum will always be greater than S naught. Now in this case, using the equation 1 and 3, right, we can say, we can drive the equation number 4. S is equal to S naught 2a minus 1. And using all of them, you can get the value of S naught, which is S1 divided by 2a minus 5. Now you can substitute the value of S naught into the equation 4, here. So you will get the final sum S equal to S1 divided by 2a plus 1 2a minus 5. So 2a minus 1 and 2a minus 5. Equation, right, for the for this sum of our um, natural numbers is the S1, right, times 2a minus 1 divided by 2a minus 5, right. Here Sn, as sum net, is equal to a times S naught. And to compute a here, because Ramanujan has done is taken both of them the same. According to him, the final sum that it will get, it is same as the S naught. And doesn't make sense because it seems like some sort of assumption. Now, but we can calculate the value of a here, right? Because if you plug in the value of a here, 1, then you'll see the equation, the sum will reduce to negative 1 by 12, right? Now, if they both are not same and we want to compute the value of a, right? Uh, then we can say Sn by S naught, it can be written as S by S naught plus 1 divided by 2. Using this equation here, you can write Sn by S naught in the form of S by S naught, right? Plus 1. Now we must now be able to compute S by S naught, and we can. So S is equal to B times of S naught. Here you can write sum of first n natural number using the S. For the S naught, you can for this series you can write this equation, right? Now, since it's contain this floor operator, so we will divide the. So first we will solve for even n, and then we'll solve for the odd n. For solving even n, we'll get S naught as this equation by 4 in the bracket and by 2 plus 1, right? And then we'll use these two equations, S naught and S naught, to compute the value of beta. And we'll label this as equation 1. Similarly, for odd n, we'll have different S naught equation, and we'll use this S naught equation and S equation to get our, our different value beta, right? Different equation for beta. So we have equation 1 and 2 for beta. Both are depending on the n. And so for n tending to infinity, we'll see the value of beta came out to be 4, right? Now, this is the same thing. Based on that, now we can plug in the value of this beta S by S naught plus 1 divided by 2. So it is 4 plus 1 divided by 2, we'll get 5 by 2. So yeah, so A is 5 by 2, right? So if A is 1, we saw Ramanujan did it, we get S is equal to negative 1 by 4. If A is 5 by 4, so it's tending to 5 by 2, we get infinity. And that makes much more sense, definitely. Because clearly negative by 12 That result is cool, but it's absurd as well. For the sum of the infinite natural numbers, the infinity make much more sense. And by going through this process that I did in the slides, we can say that the Ramanujan proof could be wrong because whatever is negative 1 by 12, that's definitely not the the sum of infinite natural number. It's something else. Right? So that's it. Thank you.